Okay, let us start the tutorial number 6. So in this tutorial I will try to redo a two-dimensional heat diffusion problem, heat conduction problem by using the sweep and with the line by line method, where we choose a direction to sweep our solution and another to another direction where we apply TDMA, right? For 2D, so we'll apply the TDMA in the y direction and sweep along the x direction, right, using something similar to the Gauss-Seidel method. Okay, so let us build our problem. We will again take a small domain comprising of 4 cells, 1, 2, 3 and 4. So here we will have say 100 Kelvin, say here 400, here say 600, 500 Kelvin. Okay, so these are all Dirichlet isothermal boundary conditions. Now what we will do is that let's make so we will use the TDMA or the tridiagonal matrix algorithm in this in this direction. Okay, and then we will sweep along this direction. Okay, so by that what do we mean? So okay, so we'll try to solve or I'll try to demonstrate how the line by line method works. So here we have defined a domain where we have Dirichlet boundary condition in all of the sides, and we have 4 cells for a simplified analysis. Here we have 100 Kelvin, 400 Kelvin, 600 and 500 Kelvin. So what we have decided is that we will apply the TDMA algorithm, or TDMA we will apply TDMA in the y direction and will sweep in the x direction, right? So we'll approximate, for example, if we are traversing in the y direction, solving for 1 and 2, then we will take a guess value of the values required for 4 and 3. Okay, so let us see how this goes. So our equation is nothing but, so after all this discretization and applying the Gauss divergence theorem, we will be finally left with something like this, assuming k is constant and uniformly spaced grid. Okay, just for simplified analysis. So dou t dou x sorry at east minus k dou t dou x at west plus okay. So now say we want to do this for each of the cells, cell number 1 2 3 4. So what about cell number 1? Let's write about cell number 1. So we do not have a neighbor in the west side and the south side, which will be replaced by the boundary values. So in the east side it will be k times okay, so there will be the areas also here, right? So this will be delta y delta x. Okay, so k delta x times delta y by dt dx will be t3 minus t1 and also assuming equally spaced grid, which means delta x will be equal to delta y. So this will help us simplify this problem. Now for the west face it will be so k times del y delta x by 2, because the distance here is delta x by 2, and here is, for example, let's straight away write 100. So t1 minus 100. Okay, so this will be negative. Now for the north north face, k delta x by delta y, then t northern will be t2 then again minus k delta x delta y by 2, okay. So this will be t1 minus 500 equal to 0. Okay, okay, so we can just simplify it by cancelling out the delta x and delta y's. So finally what are we left with? We are left with k t3 minus t1 minus 2k t1 minus 100 plus k t2 minus t1 minus 2k t1 minus 500 equal to 0. Okay. So let's just get all the t1 coefficients in one side. So it will be k plus 2k, then here plus k, then again plus 2k. Alright, is nothing but k t3 this term plus k t2 this term is done, all the terms are done. Now only the b term, right? So it will be 2k times 100 plus this term is gone, and 2k times 500 equal to, okay, so not equal to 0, I'm sorry. Alright, so finally what do we have? So we can just take the k common and get our final value. 6t1 equal to t3 plus t2 plus 200 plus 1000, right, equal to t3 plus t2 plus 1200. Okay, now we have for cell number 1 we have our equation. Similarly, we can formulate a similar thing for cell number 2, which will have neighbors of say 0.1 and 0.4. Okay, let's just quickly write them down. We'll make a box around it to this is for cell 1. Now for cell number 2 we can just use take reference of this form and just write it down. So we will have, for the only difference will be, even here the west cell will not be there, only the north cell will be, and the north cell will not be there, unlike in point 1 where the south cell was not there, south neighbor. So it will come out to be something like k times this is the east, t4 minus t2, right, t4 minus t2, the east neighbor. The west neighbor will be 2k t2 minus 100, right, it's 100 degrees Celsius, 100 Kelvin, and the top is 400, right. This is for the north, so 2k 400 minus t2, right, so this will be 400 minus t2. And finally the south face, for the south face we will have k times t2 minus t1, right, this is k t2 minus t1. Okay, so we finally have this form. Now we can rearrange it, so it will be again, so t2 will be k time k plus 2k, 3k, 4k, 5k and 6k, right, so it will be 6 sorry, let's just remove all the k because it will anyway get cancelled. So it will be 6 t2 equal to t4, this one, plus t1, plus we will have this part 2 times 100 plus 2 times 400, right. Anything else? Yeah, I think that's it. Okay, so now finally we will have for cell number 2 is 6t2 is t4 plus t1 plus 200 plus 800 is nothing but 1000, 4 to the 8. Okay, so now we have it for cell number 2 as well. Similarly, if we just use our intuitions, we can obtain the value for cell number 3 and 4, right. Let's write them down. Okay, so cell number 3 will have neighbors. What are the neighbors? Cell number 3 will have 1 and 4. Okay, so it will be 6T3 T1 plus T4 T1 and T4, and what will be the B value? B value will be 2 times 600 plus 2 times 500, right? So 2 times 600 is 1200, and 500 into twice of 500 is 1000, so it will be 2200. Now again for the fourth cell, 6T4 is nothing but the neighbors will be T3 and T2. Right, T3 and T2, and it will be 400 times 2 plus 600 times 2. This will come out to be this will come out to be 800 and 1200, that is 2000, right? So yes. Okay, so right now what we are doing is that we are just populating everything. So I am going like from 1 2 3 4 like this. Okay, so the direction will be somewhat like this. So we will propagate our solution using the TDMA method in the y direction, and then we will sweep. Okay, so for example we go from 1 to 2, then 3 to 4, right? So for example if we have something like this, 1 2 3 4, then again 5 6 7 8. Okay, so for example if we chose to do the TDMA in the x direction, then we will have to go 1 5, then we will go to 2 and 6, then we will go to 3 and 7, then we will go to 4 and 8. Okay. Or else if you want to do the TDM in the y direction, you can go to 1 2 3 4, then again go 5 6 7 8 like this. So it does not matter what the final solution is. Okay, sorry, it doesn't matter which direction you choose to sweep and which direction you want to apply TDMA. Finally the solution will be same. Okay. Okay, so now that we have all these equations, let me just write them down together, it will be helpful. So 6T1 T3 plus T2 plus 1200, 6T2 is T4 plus T1 plus 1000, 6T3 then 6T4 T3 plus T2 plus 2000. Okay, so now so we apply TDMA in the y direction, right? So in the y direction we will start from the first column, which is nothing but 1 and 2. Just give me 1 minute. Yeah, okay. So if you remember what did we do in TDMA, we did something like ATP, sorry, ATI to BT I plus 1 plus C T I minus 1 plus D, right? So AI, BI, CI and DI. Just give me 1 minute. Yeah, sorry for the interruption. Okay, yeah, so we had represented it something like this. So here so here the I plus 1 will be only this one, right? So where if I is 1, we'll have I plus 1 only this one. All this T3, for example, if you see cell number 1 and cell number 2 will be in the y direction, and whatever is not in the y direction will take the guess values, right? So we'll take a this is T3 and T4. We take T3 star, T4 star. So T3 and T4 for the T1 and T2 values will take it in the as D, right? If you remember, this will go to the constant, and TDMA is only for valid for a one dimensional operation. Okay, so so we'll first calculate P1 and Q1, right? Then we'll calculate P2 and Q2. Then we'll take Q2 is T2 will become Q2. From T2 we'll get T1, and we are done with the TDMA in the first column, right? So let us do that. So first we have to assume some guess values for the T3 and T4. So let me just draw it here. This will be helpful. So first the guess value for T3 and T4, let's assume it to be say something like 200, right? So another thing is that if you look at the problem at the first glance, all temperatures are above 100, right? Above 100 and below 600, and there is no source. So what does intuition tell us? It tells us that the temperature which is bounded by a highest and a lowest value, the temperature inside the domain can never go beyond that, right? If it goes beyond that, it violates the laws of physics. That means that without any source also the temperature is increasing, which is not possible, right? So what we can do is that we can intelligently take a guess, a proper guess value, which will help us to converge faster, right? So if we could have even taken the value of T4 and T3 as a 0, but this would have resulted in in a very slow convergence. So we will choose something in between the highest and the lowest value. Here it is bounded by 400 and 600, and in this side 100, and here 500. So it should be around something like 300 or 350, or somewhere between 200 and 300, right? So that is why we took a sort of a realistic value. So we will take a value of T3 and T4 as 200 Kelvin. Okay. So now we have to deal with the T1 and T2, right? So T1 will depend on T2. So T1 and T2 are interdependent, and T3 and T4 we already know the value because we have a guess value here of 200. So we can club it together with the constant here, right? So let's do that. So if you remember, P1 was nothing but what was P1? Just a moment. Yeah, so P1 will be B1 by A1, okay, and Q1 will be C, just a moment, let me just check it out so that I am not wrong. Yeah, so it will be Q, just okay. Let me just write the original value. Okay, yeah. So this is the formula that we have. Sorry for the delay, totally forgot about it. So P1 will be nothing but B1 by A1, and Q1 will be nothing but D1 by A1. Okay, so in this case, what is P1? So for, yeah, yes, it disappears by, you can the easy explanation is for point 1 there is nothing called point 0, right? There is no point called 0 here. Okay, so these terms where I minus 1 does not exist, this becomes a 0. Or else you can also from the previous class, if you remember, I had told you means how these things generally behave at the boundaries, very close to the boundaries, right? So if you remember, yes, so for example, something like this, right? Phi 1 is equal to some constant value, right? So T naught or some constant will be there, right? Then for phi 2 we will have something like this, like phi 2 will be something A2 phi 2 is equal to B2 phi 3 plus C2 phi 1 plus D, something like this, right? If you remember. So here what is the a value? A value will nothing it will nothing be, means this will just be a constant, so we will not have any equation for this, right? So we will start from point number 2 itself. So when we have near very close to the boundaries, we don't have the values for P means the values for the cells which are beyond the boundary, right? So if we are taking the point 1, there is nothing, no point called I minus 1. If I is equal to 1, there is no point called I minus 1 is equal to 0 in this case, right? So here in this case, because of this part becomes 0, this and this part becomes 0. And also another thing that you will see is that there is nothing called the C, no concept of C here. If you see, if we write it something like this, like AI phi I is equal to BI phi I plus 1 plus CI phi I minus 1 plus DI, then you will see that for the case where we have a boundary, so here the boundary, for example, this is the I, we will not have any I minus 1 value, right? We will not have any I minus 1 value. Rather than I minus 1 value, we will have some T naught value, that is some temperature, constant temperature value, right? So that is why we do not have any C value. So we take, for example, the C to be 0, and when we take the C to be 0, then these terms disappear. Again, can you repeat your question? Yeah. Yes. Okay. Okay. So let me just shall I derive the formula how we reached it, so it will become clear. Okay. Hmm. Yes. in direction means it does not depend actually in which direction. You can take it in the either in the x direction or the y direction. For example, yes, even in the y direction, even in the z direction, the p does not exist. So let me just give you a brief example. For example, if you take this this term, right? So 6t1 is t3 plus t2 plus 1200, right? So if you take this equation and if you see the one dimensional direction in which you are about to perform the TDMA, you have the point number 1 and point number 2, right? So here this is nothing but Ti. So Ai and something plus this will be Bi Ti plus 1, and there should be something like Ci Ti minus 1, but it is not there. So and the other thing is T3, we have taken the gas value T3 star plus 1200, right? So this acts as Di, okay. So we have this form Ai, Bi, Ci and Di, right? So we have Di, Ai, but this thing does not exist, right? So this thing does not exist. How can we put it, means how can we reconciliate with this fact, right? So we just consider that Ci is equal to 0, okay. So whatever the temperature might be beyond here, it does not matter, because in the first cell, in the boundary cell, we have taken Ci is equal to 0. So when we take Ci is equal to 0, we don't have to worry about this I minus 1 values at the boundaries, no matter which direction we take. Okay, what P and Q are? Okay, I think you means I could not explain in nicely in the previous lecture. Let me just go through it. Okay, once again I'll go through it, and I hope I will be able to make you understand. Okay, so let me just go through the derivation of how it is very short derivation. I will try to finish it in a few moments. Okay, so let us write something like Ai Ti Bi Ti plus 1 plus Ci Ti minus 1 plus Di. So this form you are familiar with, I hope so. Okay, so here the one, so there will be cells like 1, 2, 3 and going to n, right? N minus 1 and n. So these cells will be the interior cells, and these will be the boundary points. For example, if we have a something like this, so this will be the 1, 2, 3 like this, and 4 and n, and this will be n minus 1. Okay, so now say if we have a Dirichlet boundary condition where we have the T1 is equal to say 100 Kelvin, we have a boundary value specified here, and say Tn is nothing but 300 Kelvin. Okay, so we have the value here, but how can we put it in this form? So for putting it in this form, we can write something like this. Say Ai T1 is equal to nothing but 1, it's 100, right? Is 100 Kelvin, right? Because Bi, Ti, all these things are not required, right? Because we already know the value. You understand? You are getting my point? So this is some constant value, right? So at the boundary, this is some constant value. So let's write constant value, and T1 we know already. So T1 is 100. So what does this mean? This means that A1 is nothing but 1, right? What does this mean? So 1 times 100 is equal to 100. It just means that. So A1 is equal to 1, B1 and C1 is equal to 0, And what is this? So here this d1, this will be nothing but the d1, right? So if we arrange this equation, t1 is equal to b1 t2 plus c1 t0 plus d1. So these things we don't need. So we have b1 and c1 is equal to 0, and we have only left with a1 t1 is equal to d1. And so we have taken a t1 is equal to d1 by a1, which is nothing but, so d1 we have taken as 100 and a1 as 1. So this is just an elaborate way to say at the boundary we have a temperature specified. Okay, so now that we have this, so let's now see. So now if we write the t2, what will be the t2? So a2 t2, just let me just rub all these things. So this part is clear, right? How to write for the first boundary. So at the boundary it is we just cast the boundary value in the system of linear equation form that we have here, and we just what is called we just make a statement about the boundary condition that we have all the values specified. So let me write it here. So here a1 t1 is equal to d1, d1, where a1 is equal to 1 and d1 is equal to 100 Kelvin. Now going to the point number 2. So what will be point number 2? So for point number 2 we can write something like this: a2 t2 is nothing but b2 t3 plus c2 t1 plus d2, right? You are familiar with this form, right? Hello? Yeah. Okay. So now if you see that the t1 value we already know, right? So this whole thing is nothing but a known value. So this equation, what we can write? So we can write it something like this. We can write it as that t2 is nothing but a function of t3 only, right? Because we know all these things, we know this value. So t2 is a function of t3 only. Now we go to the next cell. So what is the next cell? The next cell is the t3. So we'll have a3 t3 b3 t4 plus c3 t2 plus d3. Okay, now we have the t2 and t3 and t2, where but we already know that t2 is nothing but a function of t3, right? So since it is a function of t3, it will be something like a1 something alpha t1 plus beta, something like this, right? And we can just t3, right? So we can just take it here, and what we will get finally? We will finally, if you can write the t2 in terms of t3, we can just write it like this, right? The only unknown will be, so this is a function of t3, the only unknown will be t4. So we can write that t3 is nothing but a function of t4. Okay, up to this part it's clear. So if we go on, we will see that t4 is nothing but a function of t5, then t5 is nothing but a function of t6, and finally tn will not be a function of, because tn is already known. So tn minus 1 will be function of tn. Okay, you understood what I did here? Because tn is already known, so we will only require the tn minus 1 value, right? Because tn value is already known. So now that we get the function, in this way, we can since these are all linear equations, we can formulate a equivalence to this, right? So this is the form that we get. We can write that, we can see that the fifth position value depends on the sixth position value, fourth position value depends on the fifth position value. So ith value will depend on the I plus 1th value, right? So we can write something like this. We can write Ti is nothing but a function of Ti plus 1, right? And then we can again expand it. We can not expand it, we can just write it in a different way, that Ti is nothing but Ti plus 1 plus Qi. Okay, so this what yes, actually everything here is a constant. You will get the Ti minus 1 in the previous step, so it's just straightforward to get Ti. Okay, so now you understand where the P and Q is coming from. Okay, so let me just go ahead and finally derive how to get that. To add page, yeah. So we have written something like this. Remember these three equations. So we'll let me write the three equations here. So first of all, we have AITI BITI plus 1 plus CITI minus 1 plus DI. Then we have Ti is equal to Pi Ti plus 1 plus Qi, right? And we'll do it for the previous cell also. I minus 1 is equal to Pi minus 1 Ti plus Qi minus 1. Okay. Now we will take this equation and put it back here. So let's see what we get. We will get AITI is equal to BITI plus 1 plus CI minus 1 Ti plus Qi minus 1 plus Di. Okay, now let's do some manipulations. We'll take the Ti here, so we'll have Ti is nothing but AI AI minus Ci Pi minus 1, then we'll have BI Ti plus 1 plus this will be Ci Qi minus 1 plus Di, right? And finally we'll have AI is nothing but BI by AI minus Ci Pi minus 1 Ti plus 1 and Ci Qi minus 1 plus Di by AI minus Ci Pi minus 1. Alright. So now if you see, if we compare it with, so now that we have this form, and if we compare it with this equation, we will get our Pi and Qis, right? So Pi will be nothing but Bi AI minus Ci Pi minus 1 and Qi will be nothing but Ci Qi minus 1 plus Di minus Ci Pi minus 1. Okay, so this is how we get these equations. So I hope this is clear now. So at the first cell, so for example in this cell, or for example this cell, right? So we don't have any I minus 1. So if this is I, this will be something I minus 1, this will be I plus 1, but we don't have this, right? So this is replaced by a boundary value, T boundary. Okay, so that is why we don't incorporate, we don't have a Ci coefficient, and this is the result that we get a certain type of form, right? for P1. So for P1, if you remember, so P1 will be nothing but Bi plus Ai minus Ci Pi minus 1, right? But here we already have that. Yeah, and also if you remember, yeah, A1 and D1 we have already defined here. So that is why we do not consider this Pi minus 1 term. This automatically gets vanished, and similarly also for Q1 we will only have D1 by A1. Okay. I hope it clears your doubt. Okay. So okay, yeah, so from here, right, so if you remember from so this is this point 2, there is a cell number 2 in this problem that I have toy problem that I have shown. This is the point 1 in this case, in our case, right? And here the T1 is nothing but the T boundary, right? And this whole thing is nothing but D1. Okay, so that is why we only have the P1 value is nothing but B1 by A1 and Q1 is D1 by A1. Okay, so now all the derivations are done. Let me just, is there a way to copy? Okay, so now that we have again discussed all the how all the values, how the Pi's and Q's will be computed, let me go back. Let me go back to the solving of this 2D problem. So let me just draw it here once again for convenience. Okay, so now what will be P1? P1 is nothing but B1 by A1, right? So here let me just draw. So let me draw all the B's. What are the B? So B is nothing but I plus 1. So if it's 1, this is the B. This is the B. For 2, what? There is no B. There is just C. Let me just draw C like this. And what about T3? For T3 the B will be T4, right? So this will be the B, and T4, and this will be C. Okay, so for P1 we have what? We have B by A. So we have B is 1 and A is 6, and Q1 is nothing but D1 by A. So here D1 is 1200, so 1200 by 6, how much? 200. Okay, now P2 is nothing but B1 or B2 by A2. So B2 is not there, right? So there is no B, right, in 2. So this is 0, and Q2 will be C. So C2 Q1 plus D1 A1 minus A1 minus C1 P. Okay, so sorry, this will be D2, A2 minus C2 P1, A2 minus C2 P1. Okay, so here key C2 is 1 and Q1 is 200 plus what about D2? D2 is 1000 by A2 is 6 minus C2 is 1 times P1, 1 by 6. Okay, so let me just calculate it and tell you. So it came out to be some 205.71, right? And as we know, Q2 is nothing but, and okay, Q2 is, sorry, T2 is nothing but Q2, right? So we have T2 value is 205.71. So if you see, only in the first, this is 400 Kelvin, this is 100 Kelvin, we have somewhat of a reasonable temperature, right? So 204 is a reasonable temperature. It is bounded, and what about T1? So T1 will be nothing but P1 T2 plus Q1, right? So P1 is how much? P1 is 1 by 6 times 205.71, or let's just write 206 plus what is Q1? Q1 is 200, right? So this will be 234. Okay, so 234, right? This makes sense, right? Because at the top it is bounded by 400 Kelvin and 100 Kelvin, but in the bottom we have a it is bounded by 100 and 500. So it is natural to have a higher value in the bottom one, right? So now that we have these values, these are not the correct values, right? If you remember, these are not the correct values because the neighboring cells are just guess values. So T2 star and T1 star will have, then we use them to compute P3 Q3 and Q4 P4 and do the TDMA in the second column, right? For 3 and 4, then we will do the TDMAs. Now we have done for 1 and 2, now we will do for the 4 and 3. Then we will have some values, T1, T2, T3 and T4, we will have some values, we will store them somewhere, we will again do another TDMA, another sweep, we will store again these values is for the first iteration, second iteration, we will do like this. Then we will compare these two both and see how close they are, and depending on the tolerance value we will stop our iterations. Okay, so this is yeah. So any questions till now? the line by line method? Okay. Okay then. So I will not continue to do this because this is very monotonic and it is very easy for you to do in a pen and paper mode, but I will recommend you to use some simple coding language like Python or something like that, so that you can get a hands-on experience on how to solve this kind of problems. Okay. Okay, so the another topic that sir has covered in the last week, in week number 6, is that cylindrical and polar coordinates, right? So these are quite straightforward. I will just briefly go through them. Then we will begin to see about the unsteady problems. Okay, the unsteady problems. Till now we have only seen for steady diffusion problems. Then now we will start looking at unsteady problems. Okay, so what is the cylindrical and polar coordinates? Cylindrical or polar coordinates or axisymmetric coordinates. So these are different coordinate systems that we choose so that we can easily we can so that we can reduce the dimensions of the problem, right? So for reducing the dimension of the problem, we generally take the axisymmetric case. So what does axisymmetric generally mean? So for example, if you have a pipe, and some flow is going on. Okay, let me. It's very bad drawing. Okay. So we have a pipe here, and maybe some water is flowing, right? So if you look it from this side, so if you look at the pipe from this side, what will you see? You will see a circular cross section, right? You will see a circular cross section where there will be some velocity, like for example the velocity, how will it will change. So if you have done fluid dynamics course, then for a laminar flow it is something like a parabolic profile, right? So it will be 0 around the walls, and the maximum value will be here, so U max, right? Something like this, right? So but if we just rotate, if we rotate this pipe by some degrees, say theta, the profile that we get again is similar, right? So it is invariant. So this flow it is invariant in rotation. What does it mean? It means that when you rotate the pipe flow by any degree, the properties do not change, right? So what we can do is that rather than computing the whole just a minute. For example, if you want to do a simulation of a pipe and see how the skin friction is changing and everything, all that, whatever you want to study. For example, this is the pipe that you want to study. So you can just take a particular slice of it, right? For example, let me just zoom it here. So if this is the whole cross section of your pipe and this is the center, you can just simulate this particular section, right? You just don't bother about all these things, right? If you don't bother about all these things, you rather than solving for the whole cylinder, you will be solving for a small slice, right? Small slice of the domain. So this will reduce your computational cost by a lot. So this is how we just reduce the amount of computation that we need to do using axisymmetric coordinate systems, right? So this is very similar to the 2D coordinate systems as well. if you see, there is only x and the r direction, right, which is similar to the x and y system, y coordinate system, or the Cartesian coordinate system. But here the only difference is that the areas will change. For example, if you have some cell here, say this is P, this is say N, this is south, and this will be something like east. The area at the north of the face, of the west face of the north cell will vary, right? It depends on, so the area is becomes a function of r, right? Even if we have a uniform mesh, the more farther away we will go from the origin, the more the area will be. So this is the major difference that is between a 2D cell, a 2D mesh, and a 2D Cartesian mesh and a polar axisymmetric mesh, right? So here we will have the same, the area will not be a function of y, right? It will be only if it will only be varying if we have a non-uniform mesh. Otherwise all the areas will be same. But this is not the case for axisymmetric mesh. Okay, this is the major difference. Any doubt? Yeah, please, Anand. Yeah, at center the r will be 0. Can you just repeat? Your voice is breaking actually. Okay. Okay. Let me just clarify. So at r equal to 0, your face will be something like this, right? This will be say r is equal to 0. This will be say r is equal to some delta r, but you will still have some area, right? The area will be what it will be. The area will be nothing but delta r delta theta. Yes. Yeah, it will be a sort of a line, but anyway you will have some thickness, right? For example, this will have some finite thickness. It means that some delta theta will be there. You understand? No. If r is equal to 0, at r is equal to 0, we are not interested the area at r equal to 0. We are interested in the area that is spanned by the first cell. So for example, if this is my domain, right? This is my computational domain, and this is the first cell, right? This is nothing but delta r. Okay. This is the second cell, third cell. Here the area, there will be some finite area, no matter how small the delta r is, right? Because delta r will be always greater than 0, and also delta theta will also be greater than 0. If delta theta is 0, if delta theta is also greater than 0, if delta theta becomes 0, then this will shrink. This will shrink, and this will then become a line when delta theta is 0. But in our case, we don't have delta theta equal to 0. For example, if we want to simulate a pipe, you have to either do a simulation of 45 degrees where delta theta is 45 and simulate it, right? Or else you will take something like theta is equal to 90 degree, something like 45 degree, and then simulate it. You will never have a delta theta where delta theta will be 0. If delta theta is 0 there, then it will be straightforward a 2D domain, right? So there will be no distinction between an axisymmetric mesh and a 2D mesh. You understand my point? Because the area you will be it will be computed between r is equal to 0 and r is equal to delta r, right? So this will have some length, right? So for example, if you can just if it's, say for example, delta theta is very small, we can take it as a triangle and we can just easily find the area here. So there will be a finite area no matter how small the delta theta is, until and unless the delta theta is fully 0. Okay, so this is the concept of axisymmetric mesh and polar coordinate system. I hope everybody knows. I don't think it's quite required, but still I will just give you a brief overview. We just rub it all off. Okay, I'll just briefly touch upon the topic. Okay. Okay, so polar coordinate system or cylindrical coordinate system, right? So this is a very important type of coordinate system that we generally deal with. So let me just for example, in Cartesian system we have an x and y. So polar coordinate system, you can just imagine it as a 2D system, then you extrapolate it in the third dimension, which is similar to z. For example, x and y and z direction inside the plane of the paper that I am writing, right? So unlike this x and y, we will have two other coordinate two other bases. Let me not use other terms. So other than x and y, we will have a r and something called a theta cap, or we can write it as er cap or e theta cap, right? So it depends on the direction in which you will be traveling. So in this coordinate system, you can travel in either x and y direction. So here you will be traversing either in the e theta and er direction, right? Er hat. So okay. Okay, say let this one be P. So here it will be west, it will be east, north and south, right? And from the origin, the P will be somewhere R capital P. Similarly, the N will be somewhere R capital N. Similarly, R capital S, like that, right? And we'll have a delta theta. So del theta, let's write del theta. And what will be the spacing? Spacings will be the spacing between P and the west neighbor will be something del theta small w. This will be del theta small east. Similarly, like this, like del r small s. Oh, not small s actually, it will be capital only. Similarly here, del r capital N, right? So this way you will formulate your problem. So now if you say, for example, you will have a heat diffusion problem with some source, so we can write it like this, right? So we can write it like K gradient of T at all phases, SP TP plus SC 0, right? And what will be the areas? So let's just briefly go through the areas. For the point P, we'll have four areas, right? 4 areas of this control volume. So the east area, what it will be? It will be nothing but just rub all these things so that it's a bit. Okay, let's start with we are just identifying the so this is R small s for the south boundary, this will be R small n north boundary. So what will be the area now? So the area of the east side, so AE small e will be nothing but R small n minus R small s, right? And what will be the so this is the E theta direction, and this is the ER direction, right? So this area is pointing in the right hand side in the positive E theta direction, so it will be nothing but E theta. Similarly of A west, it will be the same, Rn minus Rs times minus of E prime theta, right? Because the area vector will point to the negative E theta direction. Now coming to the north and the south, so there is some delta theta, right? So some delta theta is there, and we have the Rs and Rn. So now for the north face, what will be what will be this? This will be nothing but Rn delta theta, right? So this will be A small n is nothing but delta theta Rn, and what will be the area vector, area normal vector? It will be in the positive ER direction, right? So ER cap, and A south will be nothing but delta theta R small s ER south with a negative sign, because the area vector is pointing towards the downward direction, right? Now that we have all the directions, what is the gradient in the polar coordinate, right? So the gradient operator in the del operator in the polar coordinate system, it comes out to be something like this. Okay. Now let's break this down into its components. So let's first start with the east cell. So K east, then E cap R dou T by dou R at east face plus E cap theta 1 by R dou T by dou theta at east face. And what is the area? We will have an area vector also, right? So A east is nothing but Rn minus R south E theta cap. This is for the east face, right? So for east. Now coming to the west face will be negative Kw E cap R dou T dou R at west face plus E cap theta 1 by R dou T dou theta at west face, and Rn minus R small s E cap theta, right? And the negative sign, there is a negative sign which goes in here, right? Now for the north face, similarly we can have E cap north face and what was our area vector? Del theta Rn E cap R, del theta Rn E cap R, right? And finally for the south face, okay. So now it's quite straightforward from here, right? So SPTP plus SC equal to 0. Now we have the E theta, it will only so only the remaining part will be this dou T dou theta, this will get cancelled, right? Because E cap theta times E cap R will give you 0. Similarly here also this term will get cancelled, and here we have E cap R, right? So we have this term and this term getting cancelled, right? So finally what do we have? We will have KE and E theta will give you 1, right? So 1 by R dou T dou theta at E minus Kw 1 by R dou T dou theta at west. Okay, sorry, the areas will also be there. So Rn minus Rs, or we can just write it as we can just take a simplification and we can write it as Rn minus Rs is equal to delta R. So delta R plus Kn dou T by dou R del theta Rn minus K south dou T by dou R del theta R south plus SPTP plus SC equal to 0. Alright. Okay, I am really sorry, there will be a delta V here. because we have the volume integral here and not the surface integral. Delta V equal to 0, this will be also delta V equal to 0, right? Now what is delta V? Delta V is nothing but this volume, right? So we can take that we can assume that this distance is nothing but r of p. Okay, we can just assume that delta r is very small, and we'll take it to be sort of a square sort of a shape. So we'll take, so what will be this value? So we have delta theta, and the radius will be something like rp. Okay, and what will be this length? This is nothing but delta r, right? And what will be this length? This will be nothing but rp delta theta, del theta, right? So it is nothing but del r del theta rp. This is the volume of the cell, right? Now where were we? Yeah, so this is the equation that we got, right? So let's just write down all this all the other stuff that is needed. So here, so k east del r, this is r at east, which is nothing but r small e, right? Okay, this will be nothing but, this r will be just a centroid here, right? So it will be nothing but rp, you understand, right? So this is the east face, and this is the rp, right? The radius here will also be rp, so that is why it is rp. And we have we have dou t dou theta, which is nothing but t east minus tp divided by del theta east, right, minus kw. Yeah, please. It refers to the centroid of the cell. So yeah, if we go here, so this point, right? So this is the centroid of the cell, right? Yes. RS is the radius where the south this is the RS, right? Yes, this is the face. All the small letters that we will be using are for the phase values, and all the capital letters will be for the centroids. Yes. Because the face, because this is the face, right? Okay, let me just draw here again. Let me make it clear. It's quite haphazard. So this is the sort of a cell that we get in a polar coordinate system, and this is P, something like this. It will extend it to. So there is the centroid radius, there is the different faces here, right? So here the radius of this face will be r small s, this will be r small n, right? And we are considering, for example, the east face. Okay, we are considering this face. For so if we consider this face, so what is which radius should we take? Should we take the south one or the north one, or somewhere in between? Somewhere in between is seems to be the correct one, right? So somewhere in between is where this is nothing but RP, right? R capital P. So this is the same thing here, right? So this point is also, the radius of this point is also RP. That is why we have taken RP, because there is no concept of R small e, right? We don't have a concept of R small e, because the east is the east face spans the x direction, spans the radial coordinate system, right? So that is why we have taken RP instead of RE, because there is no concept of RE only. Okay. Okay, so let's get back. All right. So now KW will be nothing but KW delta R. It will again be RP, right? Because in the west phase also we have the same point. Now this will be T west minus, sorry, TP minus T west by delta theta W, right? So what does this actually mean? This is nothing but a distance, right? So if you look at this part, so KE delta R TE minus TP by RP. Okay. So what does this actually mean? So this is nothing but, so corresponding to this polar system will corresponding to something similar in the Cartesian coordinate system, right? So it will be something like AE. So AE will be del y times TE minus TP by delta x, right? Let me just draw it here for your so it will be something like this. Is the P now this is nothing but delta theta east, right? Sorry, not small e, it will be capital E. Okay, so delta theta capital E. So now we have to find the gradient between these 2 points, right? So comparing it with the Cartesian coordinate system, what do we get? We have P, we have capital E, capital W. This is nothing but delta XE, or in our case, let's write right. So we have assumed the gradient to compute like this, right? So TE minus TP, this part is okay. Del R is also quite intuitive because this del R is similar to what we have as del Y, right? Right. And what about the del XE? So this is the length that we need, right? So what is this actually? This is nothing but the radius, which is r capital P, times the del theta, which is nothing but rp del theta capital E, right, which goes into here. Okay, now you see the relationship between the coordinate Cartesian system and the polar coordinate system, right? So it is quite straightforward now. Now again going to the north and the south cells. Just a minute. Okay. Now for the north cell, what it will be? It will be Kn, then okay, sorry, yeah, Kn, this term, right? So it will be Kn, and what will be the area will be del theta Rn. What will be the dr, right? So here what will be the dr? Dr will be nothing but rp minus r capital N, right? Or sorry, Rn minus r capital P, and it will be nothing but Tn minus Tp. Similarly, for the south face, we have K small s del theta r small s divided by r capital P minus r capital S times Tp minus T capital S, right? And same as before, Tp plus Sc equal to 0. Now again, if we just do the same thing, that APTP is equal to AE plus T capital E plus AW T capital W plus AN T capital N plus A South T capital South plus what was it, B, right? So what will be AP? AP will be nothing but summation of all neighboring points minus of SP, right? Right? And what will be A east? A east will be nothing but K east del R RP del theta E. A west will be KW del R RP del theta W. AN will be K small n del theta Rn by Rn minus Rp, right? And A south will be K small s del theta R small s Rp minus R capital S, right? And what will be B? B will be nothing but Sc. Okay, so now you see it is quite similar to what we have done in our Cartesian coordinate system, but in polar coordinates this will be a little bit different. And also in the, if you remember, in the axisymmetric coordinate system, everything was similar to what we had in our 2D Cartesian coordinate system, but the only difference was that the area that we have for each of the cells in the these areas will be changed, right? This area will be changed as a function of the radius. Okay, so now since this is done, I will briefly touch upon the topic of unsteady problem. First we will start with the diffusion problem and see how we will solve it. Okay, so just give me 5 minutes, I will be back. Okay, so let's get back. So we'll look at a diffusion problem in this section. Let's write the general scalar transport equation that we had derived before, right? So it is nothing but rho t rho phi plus del dot rho u vector phi is equal to del dot gamma grad phi plus sp, right? So we'll just ignore this term. We'll ignore this term, and we can keep the sp, not an issue. Now that we have this term, so dou by dou t rho phi is equal to del dot gamma grad phi plus sp, right? So this is the unsteady term, right? So initially what we have done, initially for the steady problems, we only integrated in the space, right? Integrated over the volume, or did the integration over the surface area, right? So a spatial integration. So in steady problems, we only integrated over space, right? Now for the unsteady problem, we also have a time integration to do. Okay, so we also have a time integration to do here, right? So let's do the integration. So control volume dou t O phi dv, and also t and t2t plus delta t is equal to t plus delta t, control volume gamma grad phi. We have dv and dt plus t plus delta t cv sv dv dt. Okay, so now let's look at the unsteady term. Looking at the unsteady term, which is nothing but this value, we can just interchange the integrals, right? We can take the time integral inside and do the volume integral outside. So it will be something like this: control volume t plus delta t rho by dou t rho phi dt dv. Okay, so let's write, we'll write the value of phi at time t as phi naught, and t plus delta t, we'll write it as phi 1, right? Just for our convenience. Okay, so if we do this thing, so this dou by dou t rho phi dt, this whole term will turn out to be only rho phi, right? So this will be something like this: control volume rho phi from t plus delta t and dv. Okay, and again control volume, so this is rho phi at t plus delta t minus rho phi at t times dv, right? Okay, and we can just replace this integral into just a multiplication with the discrete volume, right? So it is nothing but rho phi 1 minus rho phi naught times the del V, the volume, right? So the unsteady terms become this, that is rho phi at 1 minus rho phi at 0 times delta V. Okay, so this is the unsteady term. This is how we get the unsteady term. Now we have integration of t to delta t, t to t plus delta t for the other terms also, right? For the diffusion term and the source terms also. So let's look at the diffusion term first. T plus delta t, control volume, del dot gamma grad phi times dv dt. Okay, so now we do the Gauss divergence theorem as we have done for a long time, and make it discrete, that is a summation over all the phases. So let's not write phase, let's make it as small as possible. Summation over gamma grad phi times area of the phase, right, AF. So this is at phase F, right? Now we have also a integration here, right? So we have some value at a point at time t is equal to t, and some other value at say this is the value, this is nothing but phi 1 at time t is equal to t plus delta t. Okay, and we have these two values, and we can just take a linear combination of both the values, right? If any issues comes up, please feel free to unmute and ask questions. So what we will do is that since this is an integration, we will take a linear combination of these two values. So what will we do? We will do something like this. So the diffusion term will become, we have a summation of gamma grad phi f AF which is at time 0, and also we will have another term of summation gamma grad phi A at phase F at point 1, right? So we can assume some factor to do a linear combination of the values at the two different time steps. Okay, so what does it mean? It means that we can write it something like this: f times summation gamma grad phi A at phase F at point 0 plus 1 minus f summation of gamma grad phi A at phase F at time 1. Okay, and we have to ensure that the f is always less than 1, less than or equal to 1, and greater than or equal to 0, right? So now let's just rewrite the equations that we have. We'll just ignore the source term for now. If the source term is not varying with temperature, if the dependent variable phi, the source term does not depend on time. It is only a function of space or function of phi. We can just ignore the we can just ignore the integral, right? The temporal integral. Oh, and another thing, this will be accompanied with the delta t, because we have converted this integral into a algebraic equation. So this dt will become nothing as delta t, which is the discrete time steps. Okay. So now let's write down the equation that we have, and the unsteady term will become something like this. So rho phi 1 minus rho phi naught times delta v is equal to f times summation gamma del phi a naught at all the faces plus 1 minus f summation gamma grad phi a f at time 1 times delta t. Okay. So let me again just break it down one more time. So rho phi let's assume a one dimensional problem where p and west is there and east is there. Okay. So this one we can just break it down. So this will nothing be f times gamma e phi e minus phi p by del x e times delta y, or the area, minus gamma w phi p minus phi w by del x small w delta y plus 1 minus f gamma e phi e minus phi p by del x e del y minus gamma w phi p minus phi w by del x w delta y multiplied by del t. Okay. And this whole thing will be a at time t is equal to 0 and t is equal to 1, right? So this will be nothing but phi e naught, phi p naught, phi p naught, phi w naught, and phi e1, phi p1, phi p1 and phi w1, right? Now if you look at this equation, we'll have a different type of formulation, right? So if you see for time t is equal to 0, that is the present time step, we know all these values, right? We know all these values. I am representing it with the green color. So we know this value, this value, this value, this and this, all of them we know, right? The unknown values are this and this, right? These are the unknown values. Okay. Now if we take f equal to 1, then what do we have? If we have an f equal to 1, then this whole thing will become 0, right? And f will become 1. So we can see that if we take this f equal to 1, then we have something of this kind, right? Delta t, this is not, right? And we already know all these values, right? And only unknown is this phi 1. So we can straight away get all the get the values of phi from all these known values, right? So this is a simple algebraic equation. we won't get a linear system of equations. So we can straight away get phi 1 as a function of all phi i's at some known values. But when we have f equal to 0, or when we have f equal to 0, what do we have? This whole term goes to 0, this whole term vanishes, and we are only left with this part. This will become f equal to 0, this will become 1. So when f equal to 0, let me just write it down. For f equal to 0, what will we have? We have rho phi 1 minus rho phi 0 times delta v times gamma east. Okay, let me just copy it, it will be easier. Right, and all these things are unknown now. All these things are unknown. Only the thing that is known is that the previous cell value at the point P. Okay, so now we see that there we are left with so this formulation results in simple algebraic equations, and this will result in a system of linear equations, right? So this form of solving the form where we have only one unknown and all the rest of is known, this type of form is called the explicit time stepping. And this type of form where we are left with a system of linear equation which we need to solve using some Ax is equal to b linear solver, this is called the implicit method, right? The implicit method. Now what happens when we choose some value of f which is between 0 and 1? So there is another time stepping scheme where f is taken as half, right? So both this part and this part will survive, and it will be multiplied with a factor of half, right? So this type of method is called a Crank-Nicolson method. Okay. So I have briefly given you a description of how the unsteady problems we generally solve. Okay. So in the next class, next tutorial, I will try to solve one unsteady problem, and if possible, I will prepare one Python program to show you how the solution varies from time to time in an unsteady problem. Okay. Any questions? Okay, so if there is no more questions, then I'll like to end this tutorial session, and thank you for joining this tutorial. I'll see you in the next next week. Thank you everyone. Good night. Thank you, Dipraj.